Don't throw it away. Hi everyone. Today we're gonna do chapter 5, array-based sequences of the book Data Structure and Algorithms by Goodrich. The highlights of the section that we're covering, if time permits, will be Python sequencing types, low-level arrays, dynamic arrays and amortization, efficiency of Python sequence types using array-based relational data sets. Python sequence types in this sequences classes, namely in the built-in and the likes of list, tuple, strings. If you remember our list, what is the list? It is when we have the list of things, you say fruit, what the list of fruits are apple, banana, orange. Those are lists can be made as a tuple or as a list, immutable or changeable. And then the strings, you can say like names, the strings. So Python takes strings as a array types, which each alphabet falls under index. Let's say classes. So the C falls under index 0, L index 1, A index 2, S index 3, S again index 4, E index 5, 6, S index 6. So those indexes are forms of arrays. So one can say array is a special variable which can hold more than one value at a time. If you have a list of items like car names, storing the cars in a single variable could look like this: car 1, Ford, or car 2, Ford, or car 3. But you can just put in one car and then say, okay, I have a car, Ford, or Volvo, BMW. There is a significant commonalities between these classes. Most notable, each supports indexing to access an individual element to sequences using a syntax such as SQ with the index K, SEQ with the index K, and each uses a low-level concept known as an array. To represent the sequence, however, there are significant differences in the abstraction that uses the classes represented. In a way, that instance of these classes are represented internally by Python. These classes are used to widely in Python programs, and they will become more building blocks upon which we'll develop more complex data structures. Public behavior, a proper understanding of outward semantics for classes is necessary for a good programmer. While the basic usage of lists, strings, and tuples may seem straightforward, there are several important subtleties regarding the behavior associated with these classes, such as what it means to make a copy of a sequence or to make a slice of a sequence. Having an understanding of behavior can easily lead to inadvertent bugs in a program. Therefore, we need to establish an accurate mental model for each of these classes. Remember making a copy of sequence like we did when I think we did the class in PHP, where you did extend dots list. So you adding the list, you make a copy of the new list, or you reprint the same list. And then the slicing is where you divide the list from index, let's say from start index 0 to index 6. And then, but you want to print from index 0 to 3. So you just say, let's say, okay, this is 0.3. This is considered slicing. So if you want to start from 0, that's where you start and that's where you end. From 0 until 3. And this is what you call slicing. Implementation details. A focus on internal implementation of these classes seems to go against our stated principle of object-oriented programming. In our chapter 2, we emphasize the principle of encapsulation, noting that the user of a class needs to not know about the internal details of the implementation. What it is true that one only needs to understand the syntax and semantics of a class's public interface in order to be able to write legal and correct code that uses instances of the class. The efficiency of a program depends greatly on the efficiency of the component upon which we rely. Asymptotic and experimental analysis. Remember, I think we did asymptotic on algorithm analysis. We see as asymptotic notation, it's when you look at it, it's a analysis or you compute the efficiency of the analysis or of the efficiency of the algorithm. Well, one can say association as we can say you use the mathematical tools to use in computer science to describe the efficiency and scalability of algorithm. It provides a high-level understanding of algorithm behavior, especially as the input size grows. It's answer the question: how does an algorithm runtime or space requirement change as the input size increases? So this one is help us to understand. Well, we remember when we talk about the linear time or the big O notation, linear time is square, quadratic time, constant time. Those were used using asymptotic analysis. The low-level arrays to accurately describe the way in which Python represents the sequence types, we must first discuss the aspects of low-level computer architecture. The primary memory of a computer is composed of the bits of information, bits of information. Those bits are typically grouped into large units that depend upon the precise system architecture. Such a bit unit is called a byte, which is equivalent to 8 bits. 1 byte is equal to 8 bits. So in order to have a byte, the system architecture of the computer must allocate 8 bits of it, 8 bits of information. A computer system will have a huge number of bytes of memory, and to keep the track of the information is stored in what bytes, the computer uses an abstraction known as a memory address. And effects, each byte of memory is associated with a unique number that serves as an address. More formally, the binary representation of the number serves as the address. In this way, the computer system can refer to the data in bytes, hash 2150, versus the bytes in 2157. Here we're given a diagram. These 214421, these are our memory address. That's where our alphabet or our value link to have a unique identity. So we know, okay, if the computer is looking for, if you say, I'm searching for Smanga, and the Smanga is given to the address 2144, the computer will search in this address and then find, okay, Smanga is here on 2144. A representation of a portion of a computer's memory individually parallel with a consecutive memory address. Despite the sequential number of the numbering system, computer hardware is designed in theory so that any byte of a main memory be efficiently accessed based on its memory address. In this sense, we say that a computer's main memory performs a random access memory, RAM. In essence, it is just and easy to retrieve bytes with an address memory of 8675309. As we retrieve the bytes at 309. In practice, there are complicating factors, including the use of cache and external memory. Cache is where we keep the memory. The cache is CPU where it's like where you keep your memory or your reminder. So when it makes your system to be faster. So okay, if I kept who's at number 2145, it must keep it as temporarily. So if I came back, I want to show it can easily remember, okay, who was on this number. We address some of those issues, okay, in the next chapter on 15. Using notation for arithmetic analysis, we say that any individual part of a memory can be stored or retrieved in a peak of 1, which is constant time. In generally, a programming language keeps a track of association between an identifier and the memory address in which associated value is stored. For example, identifier X might be associated with one value stored in memory, while Y is associated with another value stored in memory. A common programming task is to keep track of the sequence related to objects. E.g., we may want a video game to keep track of each top 10 scores of that game. Rather use a 10 different variable for this task. We would rather to use a single name for the group and use index number to refer to the high score in that group. A group of related variables can be stored on one after another in a contiguous portion of computer's memory. We will denote such a representation as an array. As a tangible example, a text string is stored as an ordered sequence of individual characters. In Python, each character is represented using the Unicode character set. On most computing systems, Python internally represents each Unicode character set with 16 bits. In essence, 2 bytes, which means it's 8 by 8, with 8 times 2, that gives us 16. Therefore, a 6-character string such as sample would be stored in 12 consecutive bytes of a memory. Character S containing 2 bytes, which is 2146 and 2145. Again, character A, because we have 6 characters, 1, 2, 3, 4, 5, 6, 7. That's why it gives us 12 consecutive bytes of the memory. A Python string embedded an array of characters in computer's memory. We assume that each Unicode character of the string requires 2 bytes of the memory. And our periods are indexes into the strings. We describe this array of 6 characters, even though it requires 12 bytes of memory. We refer to each location within an array as a cell. And we use an integer index to describe its location with an array, with cell numbers starting from 0, 1, 2, and so on. This is a memory address, and then these cells or indexes 0, 1, 2, these are what we call arrays. Index 1, index 0, which is S, index 1, index 2, until E. Each cell of an array must use the same number of bytes. This requirement is what allows an arbitrary cell of an array to be accessed in constant time based on it. In particular, if one knows the memory address at which an array starts, e.g. 246 in a figure 5.2, the number of bytes per element which is 2 for a Unicode character, and a desired index within the array. The appropriate memory address can be computed using the calculation. So we say start. We know if we know the start, they say start here is 246 plus a cell size. We know that it contains 2 bytes. So we say 2 times index. It's an index 4, 1, 2. So just put index 4, or can put index 5, index 3. So we say 2 times 3, that would be 6. 6 plus the start. The start, remember, it was 2, 2, 4, 2, 1, 4, 2, 1, 4, 6. So you add 6, that would be 52. So that would be 3 is there. So this will be 52. So you can find where the index is. By this formula, a cell at index 0 begins precisely the start of the array, and the cell at index 1 begins precise cell size bytes beyond the start of an array, so on. E.g., cell 4 of the index 5.2 begins at the location of 2146 plus with the size of bytes, which is 2. And then we say 4, index 4, and then when we add this 2146 plus 8, that would give a 2154. This is 4 index, so it gives us this one. Of course, the arithmetic for calculating memory address within an array can be handled automatically. Therefore, a programmer can envision a more typical high-level abstraction of an array of characters as diagram below. The easy way to find this character if we are looking for, just use indexes 0, 1, 2, 3, 4, 5. Referential arrays another motivating example. Assume that we want a medical information system to keep a track of the patient currently assigned to beds in a certain hospital. If you assume that the hospital has 200 beds, and conveniently that those beds are numbered from 0 to 100 to 199. Remember, when you say if that 200, we start at 0, so it means you're going to minus 1 of the numbers. We're left with 199. We must consider using an array-based structure to maintain the names of the patient currently assigned to those beds. E.g., in Python, we might use a list of names such as patient Rene, Joseph, Jonas, Helen, Virginia. So from this, you can use array 0, give us Rene, array 1, give us Joseph, Janet, etc. Python represents a list of table instances using an internal storage mechanism of an array of object references. At the lowest level, what is stored is the consecutive sequences of memory address at which element of the sequences reside. A high-level diagram we can easily access with these indexes. An array storing references to strings, which is what we just been shown in a diagram, although the relative size of the individual element may vary. The number of the bits used to store the memory address of each element is fixed. Each is 64 bits per address. In this way, Python can support a constant time to a list or table element based on its index. In the figure 5.4, we characterize a list of strings that are the names of the patient in hospital. It is more likely that a medical information system will manage more comprehensive information on each patient, perhaps represented as an instances of patient class. From the perspective of the list implementation, The same principle applies. The list will simply keep a sequence of references to those objects. Note as well that the reference to nine objects can be used as an element of the list to represent an empty bed in the hospital. The fact that list and tuple are referential structures is significant to the semantics of these classes. A single list instance may include multiple references to the same object as element of the list. It is possible for a single object to be an element of the two or more lists, or those lists simply stored references per two objects. As an example, when you compute a slice of list, the result is new list instances but the new list has references to the same element that are in the original list, as said in figure 5.5. The result of a command tempo or temporal is assigned to prime. This is the array start from 3 to 6. So if you start from here until 6 less than 6 minutes, and here from here until 5. When the elements of the list are mutable objects, as with the integer instances of in the figure 5.5, the fact that the two lists share element is not that significant, as neither of the list can cause a chain to be stored to be shared objects. If, for example, the command assign the temporal list to on index 215, we were executed from the configuration. That does not change existing integer object. It changes the reference in cell 2 of the temporal list to reference a different object. The index 2 has been given the value 15 of the temporal, but not the original one. Which is the index 2, which is 5. The result of the command a temp assigned to 2 upon the configuration of the portrait in figure 5. The same semantic is demonstrated when making a new list as a copy of an existing one, with a syntax such as pick up assign to a list of primes. This produces a new list that is shallow copy the reference that the same elements as in the first list. With immutable element, this point is mute if the content of the list were of a mutable type. A deep copy, meaning a new list with a new element, can be produced by using the deep copy function from the copy module. As more striking example, it is a common practice in Python to initialize an array of integer using the syntax such as counters assigned to index 0 multiplied assigned to 0 multiplied by 8. This syntax produces a list of length 8. So you created a space or a list of 8 with initialized to 0. With all the 8 elements being a value at 0, technically all the 8 elements of the data are on the same object. At first glance, the extreme level of aliases in this configuration may seem alarming. However, we rely on the fact that the reference integer is immutable. Even a command such as counters 2 and add to 1. This does not technically change the value of the existing integer instance. This computes a new integer with a value as 1 and sets cell 2 to reference the newly computed value. The resulting configuration shown in figure 5.8, where the results of command data of 2, and then we add that data to 1, add a new data as 1. As a final manifestation of the referential nature of the list, we know that the extend command is used to add all elements from the list from one list to the end of the list. This extend it does not receive copies of those elements. It receives the references to those elements. When we have a list called extras and then a list called primes. So if we use an extend, it keep the old list until all of them, and then it added a new one to those 3. So it added 23, 29, 21. I usually use prime dot extend extras. So you added the extras list at the end of it. A combined arrays in Python it emphasizes that the strings are represented using an array of character, not an array of references. We refer to this more direct representation as a combat array, because the array is storing the bits that represent the primary data character in the case of the string. Compact arrays have several advantages over referential structures in terms of computing performance. Most significantly, the overall memory usage will be much lower for compact structure, because there is no overhead devoted to the explicit storage of the sequencing of the memory references. In addition to the primary data, that is, a referential structure will typically use 64 bits for the memory address stored in the array, on top of whatever number of the bits are used to represent the object. In essence, consider the element. Also, each Unicode character stored in a compact array within a string typically requires 2 bytes. If each character were stored independently as a one character string, there will be significantly more bytes being used. As another case study, suppose we wish to store sequence of 1,064 bits integer. In theory, we might hope to use only 64 million bits. However, we estimate that a Python list will use 4 to 5 bytes, 4 to 5 times as much memory. Each element of the list will result in 64-bit memory. In Python, allow you to query an actual number of bytes being used for primary storage of any object. This is done using the get size of for a built-in function of the system module. On our system, the size of the typical integer object requires 14 bytes of the memory, well beyond the 4 bytes needed for representing the actual 64 bits. In all the list, we'll be using 18 bytes per entry rather than 4 bytes. That's compact list of integer what required. Another important advantage to a compact structure for higher performance computing is that the primary data are stored consecutively in memory. Note well that this is not the case of a referential structure. That is, even though a list maintains a careful ordering of the sequence of the memory addresses, where those elements reside in memory is not determined by list, because the working of the cache and memory hierarchies of the computers, it is often advantageous to have data stored in memory near other data that might be used in the same computation. Despite the apparent inefficiency of referential structure, we will generally be content with the convenience of Python list and sublet in this book. Primary support for compact arrays is in a modular name array That module define a class also named array, providing compact storage for arrays of primitive data types. A portrait of such an array of integer is shown in Figure 5.10, where we have the list of primes, which is 2, 3, 5, 7, 11, 13, 17, 19, with an index of 0. Means there are 8 lists. We start with index of 0, 1, 2, 3, 4, 5, 6, 7. The private interface for array classes conform mostly to that of a Python REST. However, the constructor for the array classes requires a type code as a first parameter, which is a character, and that it designates the types of data that will be stored in an array. As a tangible example, a type code I designates an array of signed integer, typically represented using a list of 16 bits each. We can declare the array shown in Figure 5.10. We assign we declare array prime, and then we give it its type with array, and this one will give us the bits information, which will say 16 bits, and then this is the list we have of primes. Because Python it was inspired by C language. Here we have a code which is B, a signed character give us typical number of bytes, which is 1, a capital B unsigned character 1, a U Unicode character 2 or 4, H, etc. We can see a I, which is a signed integer. It gives us 2 or 4 number of bytes, etc. Section 3 with dynamic array and amortization. Amortization also, you can also remember that it is an analysis or a way to use for algorithm where an occasionally operation is very slow, but for most of other operations are faster. In amortization analysis, we analyze the sequence of operation and guarantee a worst case average time that is lower than the worst case time of a particular expensive operation. Where we're using on a data structure, we calculate, okay, which one can be faster, which one can be slow. When creating a lower level array in computer system, the precise size of that array we must explicitly declare in order for the system to properly allocate a consecutive piece of the memory for each storage. Each in Figure 5.11 display an array of 12 bytes that must store a memory location of 2146 through 2157 from here to here, which 12 bytes. Because the system might dedicate a neighboring memory location to store other data, the capacity of an array cannot trivially be increased by expanding into subsequent cell. In the context of representing Python tuple or string instances, this content is no problem. Instances of those classes are immutable, so the correct size when underlying array can be fixed when the object is instantiated. Python's list class presents a more interesting abstraction. Although a list has a particular length when contrasting the class allows so as to add elements to the list. With no apparent limit to the overall capacity of the list, to provide this abstraction, Python relies on algorithms of the known as dynamic array. Dynamic array means an array, the one that we created, let's say we have 8 array, can be increased or can be decreased. So it can be dynamical, can go up and down to accommodate our need of the space. The first key providing a semantic of a dynamic array is that a list instance maintain an underlying array that often has greater capacity than the current length of the list. For example, while a user may have created a list with 5 elements or index, the system may reserve an underlying array comparable of storing a double of it, which can be 8 objects reference rather than only 5. This extra capacity make it easy to append a new element to the list by using the next available